My topic is Internet for Everything. So before I begin my talk, I would like to ask a question. How many of you actually developed some IoT products and services, or use some of the IoT gadgets at home or at work? Just raise your hand. Okay, we got few people have experience in Internet of Things, so that's good. For some people didn't get a chance to use or develop the Internet of Things, I think this is a kind of an introductory talk for you as well, to understand what's going on the market for the platforms and all those technologies around. So Internet of Things actually, I would like to give some introductions first before I focus on the technology ecosystem specifically. So Internet of Things is actually have become a buzzword for quite a few years. So you maybe heard about Internet of Things specifically, but also some related terms, just like Internet of Everything, industrial Internet of Things, machine-to-machine communication, machine-type communication, something like that. Actually, people make us believe that we're living in the era of Internet of Everything, but part of that is true. So I think Internet of Things is just a coined out from academia, originally from RFID research community back in 1999. Because there's one talk given by the director of the Auto ID lab in MIT. They just wanted to advertise or promote the use of active RFID technologies so that we can make things identifiable and make the process of the monitoring more transparent, something like that. But nowadays, I think people more and more, get more chance to be exposed to Internet of Things products and services. Just one day, we woke up and realized that many of the things actually around us became Internet of Things products and services. Just like webcams started to be called Internet of Things stuff, as well as our connected fridges and kettles, as well as the wristbands to monitor our heartbeats and blood pressure and some of the activities start to be called Internet of Things products and solutions. I think this causes some confusion, so that's why every time I talk about Internet of Things, I wanted to make some clarifications. And also, I remember one conversation I had with my colleague, which is actually my boss. He asked me why we should call everything Internet of Things, because he thought everything right now, connected to the Wi-Fi, some other stuff, those kind of gadgets, we already can do that. But why we should, use some Internet of Things technologies? I think this is a really good point. That also explains some confusion among people about this concept and technologies. And the business people would like to use this as a term to marketing their products and services. And it's really wise to make a differentiation between the post-rationalized product and services for IoT and the new product and services surrounding driven by IoT technologies. But admittedly, even the webcams, the old webcams we have been used for over around 20 years, have enjoyed the enablements of the IoT technologies. For example, we get better image sensors on the webcams. We get more power saving capability on the webcams, and got more computing power on the webcams, and got more available, accessible design resources for the webcams, for example. So there are lots of things happening. There are lots of driving forces surround that kind of old days technology. So before talking about anything else, I want to share some of the one of my favorite picture depicting the world of Internet for Everything. So this picture is kind of crowded, but it describes a lot of exciting applications that can be driven by Internet for Everything or Internet of Things. So let's just zoom in to see some of the examples right here. So in this part, we can see that we can use some connected sensors distributed on the bridge to monitor some critical structured health information in order to know some real-time information, health information about the bridge, in order to avoid some of the catastrophic some accidents that could happen, or to improve some maintenance of the bridge. So we can use Internet of Things technology on the critical structures for structural health monitoring. So that's a typical application. And if we move kind of to the agriculture side, we can deploy some sensors on the field in order to monitor some moisture and humidity of the soil in order to improve the process of the crop management, to practice the popular precision agriculture concept. And also we can deploy the sensors in a forest in order to avoid some of the wildfire. We know some sad story happened in the McMurray, but if you deploy that, some of the sensors around in the forest, we can maybe have a better notification warning system before some of the disaster happens. And another critical application of the Internet of Things is that we can deploy some of the radiation sensors surround the production line and surround the nuclear power plants. So that we can avoid, we can monitor the what's going on, whether it is normal operation or not, and also avoid some disaster that could happen. Some similar to the Fukushima disaster happened several years ago in Japan. And if we move towards the city side, we can do a lot of more interesting stuff, more exciting stuff that directly related to our lives. So many people call that smart city applications enabled by Internet of Things. So I just point out some examples right here. We can deploy some sensors on the road or surround the road to detect some of the accident. We hate that accident, right? If something happened on the road, it's just gonna, cause a lot of traffic jams. So we can deploy that sensors to give us warning messages sent out to the incoming traffic, so we're better informed of what's going on in front of us. And also we can deploy some of the sensors on the street lights in order to respond better to the weather conditions and the human presence, to save power or to make intelligent decisions or to more response to the weather conditions. So to make this thing smarter on the smart street lighting applications. And also it can improve our environments in a city in order, if you can monitor some electronic magnetic radiations as well as the noise. So we can do that, all kinds of great applications to make our life easier and better. So that's the Internet of Things applications happen on the ground or on the water. But I would like to share another two typical examples which happens in the air. The first is in the air. It's called Internet of Flying Things. Everybody knows how useful a drone could be to help our lives, especially when we heard the news about using the drones to deliver some of the packages initiated by Amazon or other big companies. It's quite useful for our everyday life. But drones can do a lot of more things. The typical ones is just for entertainment for most people, to do aerial imaging, to do the aerial selfie images, and also they can do some land management and land surveying. But most importantly, they can do something for critical tasks like search and rescue, SAR applications. And because the single drone has some limitations, if you put a swarm of drones in the sky, they can do more things collaboratively than they can do individually. So they can collaborate to search in a region to make the mission faster and easier. Because of that, nowadays the drones has really a limit on their battery. They can only fly for like 20 minutes or 30 minutes, right? Considering the speed is 60 kilometers per hour, they can only search in a region with a radius of 10 kilometers around. So if we put a lot of multiple drones together to collaboratively accomplish some task, we can do things better and we can have better results for that kind of regions. A lot of things can be done with a swarm of drones. And those drones can talk to each other. We can use Internet of Things like communication protocols to make them talk to each other, to make them relate information from one drone to another, and finally reach to our control station or ground-based station to get some information from the field of interest. So that's the flying things, internal flying things. And also, we just talk about a macroscopic world. There's a concept of internal nano things that can happen in the microscopic world. So researchers coined out the idea of using the nanoscale sensors they put in the body and monitor some of the diseases that could never be detected before, or it's really hard to cure before, and reported back the information wirelessly to the base station just sitting on the desk. And it can transmit it back, this information over the internet to the healthcare providers. So that is actually make our life even healthier, and very useful information that can be provided to the healthcare providers to cure some diseases, for example. And it's not just a fiction; it happens. It's just the technology that will happen in the future, because there's some of the sensor technology that people have to make it non-toxic and make the robot more collaboratively available if they put it in our body, something like that. Some of the technologies are still under development, but it's going to be a reality in the future. So that is actually part of the Internet of Everything application as well, in the microscopic domain. So now I think it's time to look the definition of Internet of Things. There are actually a lot of definitions proposed by either organizations or consulting companies or scholars. But luckily, we have some commonly accepted definitions. I would like to share the one I like most. So the Internet of Things defined by Gartner is the network of physical objects that contain embedded technology to communicate and sense or interact with their internal state or external environment. I would like to point out 3 keywords here: communicate, sense, or interact. So that means we can put in other words, any IoT system is actually an embedded system that should have some wired or wireless connectivity modules, as well as the sensors or actuators. In the sensors, research community, they call that transducers, but it doesn't matter, it's the same thing. You can describe the sensors or actuators together as a transducer. So that's the definition. It really captures all the features of the IoT systems we can see today. So if you see anything that the company marketing the product and services that doesn't have this kind of cannot be captured by this definition, that's probably not a strictly defined IoT system. So for the 3 keywords, I would like to start with the sensors, which is commonly considered as a bedrock of IoT system. I know a lot of people think applications as a bedrock of IoT system. That's kind of true, but it's actually the fundamental technology is built upon the sensors technology. So just let's look at one of the commonly used MEMS sensors, which is micro electromechanical system sensors, which is gyroscope. It's actually available on our phones, on our VR systems, just to sense give us some orientation to the embedded systems, and how fast it's evolved every 4 years. So we can see that the dimension shows on the left of the slides is the gyroscope, the die dimension, which is a core part of that sensor, is actually half the size than that in 4 years ago. And we can put that small size of sensors into the small embedded systems. One is called, so the couple of typical examples for those small embedded systems, sensor systems. One is smart dust, and another is eco-mode. So they came out to demonstrate the miniaturized size of an embedded system, how small it can be. And that's just not the limit. We can put all different kinds of smart dust and eco-modes together to consist of a network of sensors, either in star topology or mesh topology or ad hoc topology, so that they can collaborate with each other, exchange information, and give us a sense, distribute the sensing data, and we can have those kind of data and massage it and produce some really useful information that can never be done before. So that's the sensors technology can bring to the IoT systems. But I would like to also point out another side of the IoT, which is kind of the economic driver of IoT, I would say. Nothing, will happen without economic driver. The industry will not be interested too much about the technology if there's no monetization process happened. So that's why the economic value is really important. That's why the businesses are all put their products and services surrounding the Internet of Things. So I would like to share this figure, just giving us some projections of connected devices by 2020 among all those big companies and consulting companies. Doesn't matter. You probably heard that the statement many years ago, there are going to be 50 billions of connected devices by 2020. But unfortunately, that figure was just adjusted by most companies. So I would like to share the latest figures right now. But still, they are within the range of tens of billions of devices. That's still a huge number of connected devices. It can generate a lot of benefits surrounding those devices themselves, but also it can generate benefits from the surrounding services from those devices, because the devices are just there and they're supposed to transmit some data. So that means we have to have some other devices on the edge of the network, like the edge computer or edge router, can collect those data intelligently and process those data locally before they're sent to the cloud system. And also, we can have some series of cloud services supporting those data generated by those connected devices, as well as the applications we can create it for those kind of a data-centric applications. So a lot of stuff can be done surrounding the connected devices. So that's why I think it is very important for the survival of IoT, for the turn itself, but also for the enabling technology. We're always evolving over time. Now, I would like to focus on the technology ecosystem. So, but before doing that, I would like to differentiate between technology ecosystems and the business ecosystem. They're totally different, actually. The business ecosystem is more like including the supply chains, distributors, and customers, and competitors, some sorts of the business stuff. But I think the technology ecosystems is some kind of concept that have not been explored too much over time. And it is the phenomenon of the product and services that we have seen on the IoT market is so fragmented, and we really need to have some updated view on what's going on, or came up with a theory to analyze what's going on this fragmented market of IoT ecosystem. So it's essentially, technology ecosystem is a product platform. It could be hardware platform, it could be software platform, doesn't matter. It's generally defined, and it can defined by the core components. And all those platforms can generate some of the complementary components supporting that platforms. And hopefully, all those efforts can also generate some economic values and to be connected to some business models. So that's the technology ecosystem. Now we're looking at the IoT technology ecosystem. I know it's really hard to define, give a very clear definition of what a IoT ecosystem is. But I would like to point out some key attributes of this IoT technology ecosystem. So the first one I would like to point out is it has to support some system integration. That means your platform, standalone platform, does not have much value before you can put it into other systems and make them work together. And the second one is to support some hardware platform, because any software platform cannot live without hardware, and a hardware platform cannot live without software. But software's basis, just as we've seen how important the sensors is to the IoT applications. And the third bullet point is it has to provide essential development tools, just in order for us developers and decision makers, stakeholders in the IoT's solutions can do something out of the technology. And also it has to support some connectivity technologies. What I mean by connectivity technologies is that specifically, for example, any platform should not only support some Ethernet technology, like gigabit Ethernet technology, but also some wireless technology, connectivity technology, like Wi-Fi, like other low-power wireless connectivity modules as well. So it really depends on the applications you want to, or some target sectors you want to put your product and services in. And the last one, is to support a business model, because any ecosystem are there in order to complete some mission. It has to generate some values in a value creation chain, no matter it's value, economic value, or some impact on the open source community, for example. That's actually part of the business model surrounding any IoT technology ecosystem. And the next is the natural question we can raise about IoT technology ecosystems is what defines a good IoT technology ecosystem? So based on the previous slides, it has to be very easy to integrate into the existing and hopefully future systems. And also it has to support various hardware platforms. That means if you only support an Android platform, for example, it's better to support iOS platforms as well. And there are some ARM-based platforms available as well in the embedded system world. And it also has to be easy to use in terms of development tools and other tools in order to speed up the time to market. That's very essential to any businesses. And also it has to support various connectivity technologies. So nowadays, any module, like radio module, that they don't only support one connectivity technology, but also they support multiple of them. Like I will give an example later on. And it also has to support have to have a good number of users. I know it's really related to the business model, because for any successful business model, it turns out we have a good number of users. But the number of users is important. No matter it's commercial users or open source community users, doesn't matter. That's something keep the technology ecosystem alive and evolving. So that's the IoT technology ecosystem. But also, I think it's really hard to talk about everything surrounding IoT technology ecosystem. So I would like to narrow down to the low-power IoT technology ecosystems. Because low power is, no matter or not you realize it or not, low-power IoT is very important to the IoT embedded systems. Every example that I showed you before in the world of Internet of Everything can be realized by the low-power IoT embedded systems. So it's important for the IoT. And to understand that, what's a low-power IoT is based on the low-power or hopefully low-cost application, and also it has to have low-power standardized radio modules. A lot of research shows that the power consumption of the IoT embedded systems is actually dependent on the radio modules. So if you can turn off the radio module most of the time, you save a lot of power on the IoT embedded system. So that's why it's the dominant factor for any low-power IoT ecosystem, embedded system. So I would like to just list some very popular standardized low-power radio technologies right here. So the first one is the Bluetooth, which is actually based on the layer 1 and layer 2 technology defined by IEEE. It's called IEEE 802.15.1. And Wi-Fi Halo is a new initiative, with new amendments to the Wi-Fi standards. It is officially called IEEE 802.11ah, and I think it will be available by the end of this year or early next year. I mean, the manufacturer will put some of the fabrication of the Wi-Fi Halo compliant chips maybe early next year or late next year, because the standardization is not yet officially finished. But it has a role and a mission to play a part in the low-power IoT world. And the third one is kind of a very popular one. It's been there for many years. It's the technology built upon IEEE 802.15.4. So the markings of that technology built upon that include the Zigbee 6LoWPAN, 6-Tish, wireless HART, and ISA111A. They're just targeting different markets and different industry sectors. But the underlying technology is actually defined by IEEE 802.15.4, which is a working group defining the layer 1, layer 2 technologies in IEEE. And there are a few more. One is the Z-Wave, is built upon the radio technologies standardized by ITU-T. ITU is actually the International Telecommunication Union. It's our organization under the management of United Nations. So it's kind of international standards. So the Z-Wave technology is built upon these international standards, which is also can be considered as open standard in the communication. And the DASH7 is also open standardized radio technology. The DASH7 is actually came from the active RFID technologies. In order to, they want to put a DASH7 tag to the industry automation applications. But in 2013, they just repurposed themselves to do something more. Not only in just the industry automation, but also smart energies and advertising, so all sorts of applications. And also another one is LTE-MTC, which stands for long-term evolution machine type communication. I think most of you have used some LTE mobile phones, right? So actually, if you know, the 4G system is actually based on LTE, advanced standard. So LTE is a very complex standard set, and one of the standards is for the Internet of Things communications. So the organization behind the LTE wants to make sure they can utilize the infrastructure of LTE to serve IoT communications, which is low cost, low speed, somehow for machine-to-machine communication. So that's why it's called generally LTE-MTC. And another gradually popular technology related to that to provide the long-range communication for IoTs, low-power IoT embedded systems is called a narrowband IoT. And several examples are, several ecosystems are built upon that. One is LoRa, and other is weightless. And I think another successful example is a Sigfox. You probably heard that in the news. They deployed some of the IoT infrastructure in Europe quite successfully. But all those technologies, LoRa, weightless, or Sigfox are actually have the same type of communication standards, which conforms to the narrowband IoT. And LTE also has another stream of discussing how they can put LTEs amendments in order to fit that narrowband IoT, which consume the less power than the LTE-MTC. And category machine, that kind of a type of the mobile systems. So we've talked about a lot of radio technologies. I think before I just dive into some of the models of all those technologies follow, I would like to propose the framework, which is that can be used to describe the low-power IoT technology ecosystems. So this is actually a cubic view of all those consisting of technology IoT building blocks, as well as the vertical business segments, as well as the market demands and business models. So I would like to start with the front view of this framework, right from the bottom. So we can see that open standards is very important building blocks, and actually it has a lot of standards defining the sensors operations, the sensor standards, how to manufacture the sensors and interface from one sensor to another sensor, for example, and from one sensor to the main board, those kind of things. And also the open standards for system integration standards. And also some bunch of standards for interoperability between the devices. One example is that how to make sure different devices running different operating systems, something, they can talk to each other. So that belongs to the interoperation standards. And right above that, most of the time, we will build our embedded systems with some protocol stacks. Because we're talking about the communication, most of the time, it's wireless communication for the IoT embedded systems. That's the most popular option for that. And we have to use some protocol stack. Either it's TCP/IP protocol or other protocol built upon some Bluetooth, Zigbee, Z-Wave, what I talked about before. We have to use some protocol stacks. And we also have to use some hardware components as well as some of the libraries that can make things work. So I call that hardware platform. And also, we should follow some of the software framework, no matter it's a very simple one or complex one, that join different components together in order to allow us to create some of the IoT apps to do something. And all the apps, doesn't matter what kind of app it is, it has to provide some of the data to the higher level application, the business logics. So it's related to a lot of business surrounding that. The protocol stacks and apps creation is related to software service business. And the data connectivity, that means how we transmit data from one device to another or from one device to the cloud center, is actually brought by the internet service business. So you probably have seen that there is a service provided by Rogers, provide you the smart home, and they call that Internet of Things product and services. So that's kind of a service I'm talking about. And also we have data service business. That means we take care of the sensor data from individual devices or from a bunch of devices connected together. And we have to do something out of that, to do some analysis, to do some storage, to visualize those data. So that's the service provided by data service business providers. And we have cloud service business. I think that's one kind of a typical business. For example, we have Amazon AWS IoT. That's just one of the new product offering since last year, I believe. And also the IBM Bluemix. They're all built upon the IoT solutions in terms of cloud service business. And we have also application solution business. That means put things together. I don't care about which technology we're going to use. We care about what kind of a solution it can provide. For example, the water monitoring. For example, how to monitor the radio levels on the nuclear power plants, something like that, or on the production line. So to provide that application-specific solution to do some business surrounding that. So that's the application solution business I'm talking about. And cybersecurity is very important. Cybersecurity can relate all those components. You've seen that in IoT building blocks. So last Friday, just 1 week ago, we probably heard that the internet services were brought down on the Twitter, on Netflix, right? And that's actually from the DDoS attacks, from the malicious attackers. They're using a lot of hacked IoT appliances. So your connected kettle, your connected fridges can be, or connected webcams can be taken advantage to initiate such kind of a DDoS attack to bring the service down. DDoS attack is very simple to initiate, but it has to use some botnet to do that. So IoT appliances or IoT gadgets are now become the target. So we're not aware of what's happening on our IoT gadgets. So that's the one example, typical examples. If you look at the Shodan, I think some people maybe have looked at that before. They're exposed some internet-connected devices, which is also part of the IoT devices that can be easily hacked. So there's some of the websites showing all those devices. And the hackers can take advantage of those information and put that in botnet to do some of the DDoS attacks. So that's just one example. There are many other things we have to taken care of. But don't be panicked, because I believe the Linus Torvalds the statements that we have to build something first before we think about the security out of that. And there's actually, if you follow some of the best practice of security, everything can be protected in a reasonable scale. So that's a cybersecurity business. And also, we have some traditional businesses like manufacturing the hardware of the platform, manufacturing the chips, manufacturing the circuits you design. So all those things. And also the system integrators based on those hardware components. All those kind of traditional businesses. And also, all those businesses have to survive in order to, they should have a successful business model. That's the front view tells us. And also, it has to follow some market demands. That's the right view tells us. So I think it gives us some fair amount of views on what we should consider surrounding the technical building blocks of IoT, as well as some business considerations surrounding that. So I would like to show in kind of a picturesque way of what we have for IoT technology ecosystems. So we can see a lot of brands and big names attached to some of the ecosystems sitting there. So let's just look at the IoT on the top of these slides. So we have IoTivity, we have AllJoyn. So those are two kind of a Linux Foundation managed project, which is under the Open Connectivity Foundation's management. And AllJoyn was initiated by All-Scene Alliance, and it's just recently merged to the Open Connectivity Foundation on October 10th, just this month. But it's still, I just put the logo there for the perspective of the creation of the AllJoyn project. And it's all open source. And IoTivity and AllJoyn can actually, it's open source. They're open source projects providing some communication protocols, providing some of the software frameworks that can make your development of the IoT embedded system easier. So I'll talk about that later. And we have the Brillo and the Weave, released by Google officially this year to provide some of the easy-to-use development process built upon their Brillo operating systems and the Weave communication protocol framework for the IoT systems. But it's mainly targeted for like the Android and other Linux-based operating systems. And we have LTE, that's just what I talked about before, and the LoRa, Sigfox, and Waitlist we have talked about. And on the right side, we have all those, the complete list of those technology ecosystems, like the wireless HART, ISA100A, which are actually targeting the manufacturing automation system. They have developed some protocols to ensure the reliability that it can never be easily be done by just for the ecosystem, for the communication protocols built upon for the home automation applications like the Zigbee or Z-Wave. But it's still, they have a fair amount of the reliability for sure. So they have basically they have different target industry sectors. But I want to point out three things right here I didn't introduce before. One is InNotion, which is actually is for the automation system that is built upon the energy harvesting technologies. Because there are a bunch of sensor-based embedded devices that doesn't need a lot of battery. They just need some simple, simple scenario, just transmit one chunk of information to the base station, and that's it. So that's something we can be done by using the energy harvesting technologies. Even the energy harvesting sources could be initiated by the mechanical movements, or it can be initiated by some of the chemical reactions. And Kentucky and Riot are actually two popular operating systems nowadays, especially in the research community. They're totally open source, but actually they're not created by some industry players. They're created by some of the academics. So they're sitting there. They can actually do a lot of things. We can actually do a lot of things based on the simulation tools and the operating system and the supported hardware platforms supported by that. And the Riot is a real-time operating system because we don't have a real-time operating system just for IoT before. So somebody created a Riot for that kind of a niche market. And of course, they have some commercial users. We can do a lot of things based on those two projects and two ecosystems created by them. And another one is ARM Mbed. ARM Mbed is an ARM-based ecosystem that is similar to Raspberry Pi, but I wouldn't put that analogy because there are still some differences. ARM Mbed is actually very targeted to the low-power Cortex-M technology-based platforms. And they provide not only operating system, but also the cloud services and also some of the IPs for the manufacturers and for developers. So that's the thing. And then I think I should categorize what's the kind of models that's actually working for those IoT, low-power IoT technology ecosystems. I would like to propose 4 models right here. The first one is semiconductor-driven model. And the second one is data service-driven model. And third one is vertical application-driven model. And the last one is framework-driven model. I will talk about one by one. Oops. Okay, it takes some time. So the first one is semiconductor-driven model. This actually, this model, any ecosystem following this model provides a platform driven by semiconductor-related industries. For example, if you use some of the chip, like ARM-based chip, the manufacturer of that chip will provide some libraries, software libraries, and also development tools, as well as another tools related to that to make our development easier. For the target users could be developers and system integrators for that. So this is a traditional model, I would say, and a lot of ecosystems follow this model. Like the Bluetooth, Zigbee, Wi-Fi, Halo, actually, believe it or not, they're following the semiconductor-driven model because any of those ecosystems cannot exist without any hardware chip. So it has to have some hardware chips to support those protocols, especially their communication protocols running some of the, need some support of layer 1, layer 2 algorithms following the 7-layer OSI model. And they have some common features. The first one I would like to point out is we should have some hardware fabrication support for this model. And we should have some chip-level IP cores for the model, as well as board-level support. So let's look at some of the, just one example from ARM. So ARM just released, I think recently released the Cordial Radio IP, which is a design of, for some of the radio module chip. And they can support Bluetooth, it can support Thread, they can support Zigbee. It's just announced a couple of days before, Zigbee Alliance just make announcement that it had collaboration with ARM to make sure they can, the radio, Cordial Radio IP can include the Zigbee 3.0 standards. And built upon that, we can have some boards, hardware boards, and we can have some operating system support that boards, and we can have some applications working with that hardware platform. So this actually captures some of the features of the technology ecosystem. We should have some hardware core, we should have some software stack and open standards, as well as the application profiles in order to make the, everything work specifically for every kind of applications. So that's the application profiles. And I would like to talk about the second model, which is data service-driven model, which is kind of straightforward as I talked about when before in the previous slide. This model is actually for the platforms targeting at providing the service for the data security, for the data messaging, and storage, as well as visualization, analytics, as well as the schema. So they can provide all those services built upon the sensing data. Some typical examples are Amazon AWT IoT, IBM Bluemix, Google Cloud Platform, If This and That, FTTT, and ThinkSpeak. So there's a couple of small players sitting there. I just want to point out that. We shouldn't ignore that. And they have some common features, like they provide all kind of cloud-based data services, and they provide some connectivity, connector APIs in order to better integrate it to our any software platforms, and they provide some data management functions. So the third one is really easy to understand. It's vertical application-driven model. That means the ecosystem itself has to serve some of the specific application domains. The common features include that it has to have some target industry sector, and it has to have some established market share of that sector, and it has to support some of the hardware software platforms, and also support for product certification. And some examples include the wireless HART ISA 111A, which are specifically targeted at manufacturing automation systems. And the Dutch 7 targeting some kind of building automation systems, smart energy, smart homes, and automotive systems, something like that. And AllJoyn, Thread, Zigbee, Bluetooth are actually have our target market for home automation systems. And the Z-Wave Innotion targeted at industrial automation systems. And ANT, this is just one technology that invented many years ago, is for the healthcare systems, which is used by Garmin, like the smart wristbands. Right nowadays, they're using partially of using the ANT technology. So the last one is framework-driven model. So the framework-driven model is about to provide the software frameworks for an IoT system. I think it is a smart strategy if any technology ecosystem using this model, because it's supposed to be hardware platform agnostic. It provides some framework. Doesn't matter what kind of hardware you are using. They can all work together by using the software framework provided by the by those players, by those example software framework players. And it has to support some on the SDK and the tools. And also it supports some business ecosystems. So some examples right here are AllJoyn, Thread, Brillo, plus Weave, as well as Kentucky in the right. So some are, most of them are initiated by the companies, but a couple of them, like Kentucky in the right, are initiated by the research community. But still, they can serve a lot of things for the commercial purposes for IoT product and services. So I would like to point out one framework for you is the AllJoyn framework, which is currently considered as kind of a successful framework existing nowadays. So the definition or description of the AllJoyn is actually an open source software framework that can make it easier for devices and apps to discover and communicate with each other. And also, it is actually hardware agnostic. So it doesn't matter what kind of transport layer, what kind of radio technologies you are using, what kind of manufacturer of the chip you are using. They can all work together with the software, framework, provide AllJoyn software framework. And also, the AllJoyn framework, as I summarized before, is actually follows a couple of models I proposed. One is vertical application, because it's targeting home automation systems, and also these framework-driven models. And it actually connects to all essential elements in the proposed framework that I showed you before. You can generate a lot of opportunities for related business by using this framework. So I would like to show you the framework itself, in the high-level architecture. So this is the AllJoyn software framework in a block diagram, we can have, for example, for any IoT, low-power IoT ecosystem, technology ecosystem, we have some physical layer. No matter it's Wi-Fi, no matter it's Zigbee, no matter it's Ethernet or Bluetooth, it's the physical layer stuff. And we have the operating system. It could be Linux, it could be other just the real-time operating systems. But above that is the software framework provides you. So we have the core library supporting all those essential functions like the discovery and the advertising of the other devices, as well as the connection APIs, and also the security APIs. For example, it can be very useful to secure our data transmission. And we have the router and the gateway support, and in terms of the software, to provide the different roles in the architecture of the IoT network. And above that, we have the service framework providing the, targeting different applications, capture the essential services used by different applications. For example, the onboarding, control panel, localization, and those, as well as lightning service framework. And so we can build upon those modules in the service framework to do some applications. And if you put everything together, for example, all the gadgets running the AllJoyn framework enabled application, we can make them talk to each other. They can understand each other with no problem. We can use one app to control everything, ideally, with our phone. And they can transmit all those things to the cloud or to another machine, which is far from the control center. So we can use the gateway to do that. To summarize, we have talked about the Internet of Everything technology ecosystem. And we talk about the conceptual framework that can help us understand the different things from business perspective and from technology perspective. And we can have better understanding by analyzing what's the principles working on the fragmented technology ecosystems by using the four models proposed. And also we can have we can say that any technology ecosystem does not have to follow just the one model, but also to follow multiple models, because it's possible. That's why I put there's some overlaps between the models. And the four models are just the main models from my observation, but it might be other models existing because we are talking about a broad spectrum of IoT businesses. So that's all for my talk. Thanks very much.
Thank you very much.